Hi there. In this video, we'll be going through a bit of an introduction to signal processing. What is it? Why do we need to do it? How can we do it? And what are some of the different forms that signal processing can take on? Well, first off, what is signal processing? Essentially, what we're trying to do is apply a whole lot of mathematical operations to signals. These might be to analyze a signal or manipulate a signal or clear up a signal in some way. There's lots of different operations and lots of different signals we can apply these to as well. For example, we might have an audio signal that's got some background noise in it, and we want to remove that background noise and make the speech clearer. I often do this if I'm doing video recordings in the lab. There's too much background noise and hum and things from things going on, so I want to remove that. We might be joining two different signals together. For example, my videos, I take videos in front of a green screen and I use chroma key and remove that green screen and overlay this with my lecture notes. But there's lots of other ways you can combine signals together as well. In video editing, in audio editing, where you're adding multiple signals together, lots of different forms of it. And other things like segmentation within a data set. And we'll be looking at some examples later, how we can look for key features within some signals or with some data and extract information from them as a result. Now, there's two main ways or types of signal processing that we'll be briefly mentioning. One is the analog signal processing, where we use circuit components like resistors and capacitors, inductors, op amps, those sort of things. We'll mention that in passing, but we won't be going into that really in any detail because this isn't an analog electronics course. Then we'll go on to digital signal processing, which is what we use very commonly to edit our digital photographs, to edit digital video, to edit digital audio, and edit any of our other sensors and do signal processing on those. In DSP, we're using computer systems to do all this processing for us. So just by way of passing, analog signal processing, we can build filters that can filter out certain frequencies of noise quite easily using a few components, like some resistors and capacitors that we have here. And using this, we can create a low-pass filter circuit or high-pass filter circuit in different arrangements. At some point, you may have come across one of these, a graphic equalizer. And basically the idea behind a graphic equalizer is it allows you to attenuate or boost different frequencies based on the sound that's going in to the sound that's going out. If there's a certain frequency you don't like, you can drop that one down and even cut it out completely. And so this is one way that in an analog sense, we can apply these concepts of signal processing and signal conditioning. We can remove frequencies or we can boost frequencies. Essentially a form of filtering. Let's move over now to the digital side of things. And in the digital side of things, we're using digital signal processing. And so we still have some of the same similarities with the analog signal processing and the analog systems. For example, we have some sort of physical variable that we need to read in still. And we've had a look at this in the past, that it might be sound, it might be distance, it might be light, might be a range of other things, force, for example. Now, to read in that variable, we sample it with a sensor. So that process is called sampling. Now, quite often we'll have some sort of an analog filter connected to that sensor. That filter might be what we call an anti-aliasing filter. And basically that filter allows us to remove any high frequency noise that's outside the general frequency that the sensor samples at. We don't need a whole lot of noise coupled into our signal. So, for example, if our main signal is capturing at 100 to 200 hertz, or that's the sort of frequency we're looking at, and we had some noise at 5 kilohertz, well, we want to filter some of that out so it doesn't alias our signal. We then read it into an analog to digital converter, and that analog to digital converter quantizes it, and it basically takes all those continuous voltage values and puts them in a series of tiny little digital buckets. And once we've done that, we've quantized our signal and we've got it in a digital form. Then we're free to apply whatever DSP sort of algorithms we want to that digital data, because now we're in the digital domain. And now we can apply digital processing techniques to our digital data. Before we jump straight into DSP, let me just highlight one thing about continuous time versus discrete time signals. Now, these continuous time signals are essentially in our analog domain. And so you see that waveform there, the sine wave, that's continuous. So it keeps on changing with time. Now, when we've got our digital systems, we've got discrete time signals, where we basically take samples at discrete moments in time. Now, these might be very short. They might be, we take a sample every 100 microseconds or something like that, or even faster than that. So they might be quite short, but they're still discrete. They're not continuous. And so we have samples taken at moments in time. Now, this is true for digital video, it's true for digital audio, it's true for sampling any of our other sensors as well. Now, for example, our camera might record at 60 frames per second or 30 frames per second, depending on what camera system we're using. Let's get into DSP. We know that there's many different types of signals. Everything from images, so 2D images, through to video, through the audio, through to we can store our signals as text files or CSV files, where we have line after line after line of sensor data in there. And this data is changing with time and or space as we sample it over time, and as we collect it, as potentially we move around and make various measurements at different points. Now, this data is coming from the real world, so it won't be perfectly clean. As much as we might like to, we're not just sampling a single signal. There's lots of signals out there and lots of signals that we'll be getting in with the thing that we're actually trying to sample. And so one of the key roles in DSP is trying to get rid of these other signals that we don't want and to focus on the signal that we do want. Having said that, there's lots of applications of a DSP in improving our signals in some way. For example, when we're talking about audio, we might be removing unwanted signals, background noise or hum or something like that in the signal. We can use DSP for multiplexing signals. For example, if we've got a single wire or a single pair of wires and we want several phone conversations to go through that one wire, we can multiplex them over time or over frequency bands. If our signals are too large or we want to store them in smaller areas, we can use DSP to compress signals. Or if we want to do echo cancellation, like when you've got long distance calls and you don't want the echo of your voice from the other end coming back to you because it's a bit of delay. Our ears do echo cancellation along with our brain, but when there's that delay, that echo cancellation for us doesn't work and we need to do it digitally. If we're trying to improve how something sounds, we might add in extra reverberation while people are singing to make their voice sound more full. Or we might mix in different audio tracks with other audio tracks to make what we're hearing sound even better. We might have multiple instruments or multiple noise sound sources that we're trying to balance with each other. Or we might be trying to clear up audio signals. For example, if we're designing a hearing aid, Dennis in our department's done work in this area in the past and creating higher quality aids that people can hear using digital signal processing applied within them. Or we might be trying to do applications where we're trying to understand what humans are saying, where we're trying to convert audio signals to text. DSP also has lots of applications for images and video processing. For example, in medical imaging, where we're using MRI or CAT scans and using those to look at different layers and do segmentation, highlighting key areas within those different layers. There's a whole lot of other image-based operations, everything from controlling white balance and brightness, contrast, sharpening images and de-sharpening images, segmenting images. We'll give some examples later on of some of these different things. One thing that came out in 2022 was these magic erase functions where you can, for Pixel phones and iPhones, where you can highlight areas of photo you want to erase, and it basically takes people out that are photobombing your photos. All of these things are applications of DSP. And for these non-visual and non-audio sensors, there's also applications of DSP as well. For example, if you're trying to measure the frequency of a signal, for example, if you've got a strain gauge that's oscillating away and you're trying to measure what frequency it's oscillating at, we can use DSP for that. Or we might have some high frequency noise that's been coupled into a particular signal. For example, our our platform might be vibrating and we want to remove that vibration and decouple it from the actual signal data that we're trying to extract. We might have some noise, for example, from power lines that have been coupled in, and we want to remove that 50 hertz or 60 hertz hum, depending on what country that we live in. Or we might want to do some auto classification of signals or correlating data between different signals. Sometimes some sensors work well for certain applications, but not so well for others. And so we can do something that we call sensor fusion, where we combine the best of different elements of sensors together to give us a more complete picture.